reminder of what we did yesterday. I think I went a little bit too fast at the end, so let me explain this again. So reminder. Also, we talked for 3 hours, so there was a lot of material. Okay, so what are we trying to do? So H bar, that's a learning rule. So it's a map from x, y to the n to y to the x. Okay, so that's the learning rule. Okay, so that's the main object. That's what we are trying to design. What do we have to design this? What we have is there is some unknown measure mu on x, y. And what we have is a data set S, which is Z1 up to Zn, sample from U to Zn. Okay, so that's a data set. And so the rule, the learning, the classification algorithm that we're going to use is H bar on S. And what we care about is the loss of L mu of H, defined to be the expectation on new sample Z from mu of L H. Okay. And what is this? Okay, this is this abuse of notation where this is equal to the same thing as L of H of X Y. Okay, so L is a loss function, so L goes from Y to Y to 0. Okay, it assigns to any pair of outputs whether the two outputs are close to each other. Very good. And what we said is what we care about mostly is generalization. So generalization, I'm going to introduce a notation for it. So generalization, let's see, on a data set S of the learning rule H bar with respect to the distribution mu. That's the following quantity. It's, let me also remind you, the empirical measure notation, mu hat m, this is 1 over m sum for I equals 1 to m of the point mass at the Zi. Okay, so that's the empirical measure. And what we care about is, let me see, L mu of H bar S minus L mu hat M of H bar S. Okay, so this is the main object. Yes?
With the most, it's not necessary from Y to Y, right? Or Y by Y, because, for example, the logistic regression, you have sample 0 or 1.
Right. So you can imagine in logistic regression that Y is interval 0, 1, but it turns out that the measure mu is supported only on zeros and ones. Okay, so this is what we care about. Why do we care about this? Let's say this is bounded by, I don't know, 0.1. Then what happens is that your true loss is bounded by your empirical loss plus 0.1. So what you want is for this thing to be small. So that if this is small, then this is small also. And what we did yesterday is we upper bounded this. So this is upper bounded by, let's say, the supremum over H in script H, L mu of little h minus L mu at n of little h. Okay, so this is assuming, of course, that H bar is in script H. Okay, so say we are searching in a certain function class, H to script H. Then this inequality is just trivially true. Okay. And now this quantity, you can view it as a uniform law of large numbers. Okay, so let's introduce a notation for this. So this, I'm going to define it to be the generalization on S of the function class H. Okay. And this is uniform law of large numbers. right? The law of large numbers tell you exactly that L mu hat M is going to converge to L mu for any fixed h. But now you want it to for all of them simultaneously. Okay, so that's why it's non-trivial. It's a key result from yesterday. Key result was the following. Priority at least one minus delta with respect to the sampling of S. What we have is that the generalization of the function class H, of the hypothesis class H, this is upper bounded by 2 times the empirical Rademacher H of F plus, let's say 4 times square root log 1 over delta over M, where F is the loss class, where F is the loss class, which means the following. F is a set of map from Z to L of H Z, for some H in H. And I'm going to use another pen. Okay, and remember the Rademacher, the empirical Rademacher, S on F. This is just the expectation over random signs. Epsilon I is our random signs of the supremum over F in F of 1 over M, the sum for I equals 1 to M of epsilon I F of the I. Okay. So this is how well does your function class correlate with random noise. And we saw that the generalization is bounded by this, how well you can correlate random noise, plus the concentration term square root log 1 over delta over M. Okay, so this is really what we did yesterday, basically all of what we did yesterday. Then we did some application where we tried to compute this for linear classifiers or for linear regression. Okay, so now is a good time to ask, I'm going to assume, yeah, that all of this is in domain. Okay, and you remember what we like is to compute the Rademacher complexity of the hypothesis class H, not of the loss class. And for this we have the contraction lemma. So the contraction lemma, what the contraction lemma was saying is the following. So if L, let's say, dot Y is Lipschitz, then the empirical Rademacher of the loss class is upper bounded by the empirical Rademacher of the hypothesis class. Okay, and remember, in all we do, Y is a subset of R. Okay, Y is a subset of R. Maybe just the field with 2 elements or the interval 0, 1. Okay, okay. Yeah.
So you say the high-level idea of the Rademacher complexity is how well the function can fit random noise.
Yes. Yes, exactly. Yeah. You see, those epsilon, to have this to be big, you would like F to just match the sign of epsilon I. So if on any sample I can decide it's either +1 or -1, then I have all the flexibility in the world. And if you remember the first lecture, I opened with the need for inductive bias. If you don't have inductive bias, there is no way you're going to have small sample complexity. So this is exactly what's happening here. If you don't have inductive bias, if you can do anything, then this is going to be large, and there is no generalization. Remember the example of the cube, right? So the example, bad example for generalization is the example of the cube. So if x is sampled uniformly on 0, 1 to the n, and you're trying to predict just y, which are zeros and ones, no. I mean, you will never see twice the same sample. You know, some 0 is going to be a 1 somewhere. So you're never going to see twice the same sample. So you need to say something like, you know, if I have a bunch of, you know, if I have this pattern 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, and this one 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0. I need to say that, you know, my hypothesis cannot change too much on those two samples. There is just one flip here. If anything can happen, then okay, I can never generalize unless I have seen every point. Sometimes people call this no free lunch theorem. And it's even, no free lunch theorem is even more stupid. It's this example that I told you. If you have just points on the line, you know, and then I give you a new point, if you don't know anything about the function, how can you tell, you know, what value is going to take there? You cannot say anything. Okay, good. So, let me see. Okay, so now I will do VC dimension again, because I did it too fast.
Sébastien, in the contraction lemma, it's any Lipschitz function or it's one Lipschitz contraction?
Say again?
In the contraction lemma, it's one Lipschitz function or any Lipschitz?
Yeah, one
One
Lipschitz. Yeah. So we are still in chapter 2. So we are still in 2, and this is subsection 5, and on to the VC dimension. Okay. So we care here about binary classification. With 0, 1 loss. This is the most natural loss for binary classification. So the point is, with a 0, 1 loss, it is Lipschitz if you only output zeros and ones. Okay. It's not Lipschitz if you output a real value, but it's Lipschitz if you only output zeros and ones. Okay, so this is Lipschitz. It's kind of stupid, but Lipschitz on 0, 1. Okay. So I can apply the contraction lemma. So what we get is the Rademacher, the empirical Rademacher of the loss class is upper bounded by the empirical Rademacher of the hypothesis class. And what is this quantity? This quantity is 1 over m, the expectation over the epsilon I, of the supremum over h in h, of the sum epsilon I, h of xi. Okay. So now let's look at this term. Okay, and just remember your basic probability theory. This is a sum of independent summands. In fact, not but independent summands. H right is from 0, 1 to 0 to the x. Right? So H, it's either zeros or ones. Okay. So the variance of these things is bounded by it's 1. It's bounded by 1. So by the CLT, we expect square root n, right? I mean the normalization square root n times the Gaussian. Time in n01. Okay. And now I just have many Gaussians like this. But you know, if I have, let's say, n Gaussians, okay, if I have one Gaussian, it's most likely going to be, you know, at most, its value is going to be at most 3, with very high probability. If I have n Gaussian, the value is going to be at most square root log n, square root 2 log n. Okay. Remember the Gaussian, the density is e to the minus x squared over 2. So if I put square root 2 log n in this PDF, then I get the probability which is like 1 over n, which is going to kill the union bound over n element. Okay. So square root 2 log n, it's a value that the maximum of n Gaussian is going to take. So here I have many Gaussians. A stupid bound would be to say, okay, how many? Well, it's the size of h. But you can be a bit more subtle. How many? Well, it just depends on the value of h on your sample. So this is going to be bounded. You see there is a square root n that cancels with this square root n. So you get 1 over square root n times square root 2 log. And now log of what? Log of the size of the number of vectors like this. So log of the size of h of x1, h of xm, h in h. And this is the set. Okay, so this is what we expect from this argument. And in fact, this is true. Okay, so this is called Massar's lemma. But it's really well, it's kind of obvious, just because of the CLT. Okay. So now we see that for binary classification, what matters is the size of this set, which is exactly the number of patterns of zeros and ones that you can get on the sample. Now let's introduce application. So the gross function pi m of h. This is the largest size that you can get over all data set. So this is the let's say maximum over all x1 x to the m of this thing. H of x1 to h of xm h in h. Okay, so it's a number of random, not random, a number of signed patterns that you can get on a sample of size 10. Okay, and just to make sure that we are on the same page, what is a trivial upper bound on this quantity? What's the largest value that this can take? Yes. Good. Just to make sure we are all on the same page, this is at most 2 to the n. Okay. That's good. But if it's 2 to the n, then we are in bad shape because log of 2 to the m is going to be n, which will cancel with this m. And then we don't get that the Rademacher goes to 0. So if this is 2 to the m, there is no generalization. Okay. If this is exponential in m, no generalization. If this is polynomial in n, then we generalize. Okay, because of this theorem plus this bound. Let me say this again. To have generalization, we want pi m h to be polynomial in now comes in a really beautiful lemma. This is a Sauer-Scheller lemma. Which tells us the following. Pi m of h is, let's say, of order, it's a big O, some constant, I don't want to specify it. You can say 10 if you want. It's less than that. M to the d, so it's polynomial, whereas the exponent is d. And what is d? Where d is the largest m such that pi m h is 2 to the m. So take the largest sample size where you cannot obtain any sign pattern. This is also called a set which is being shattered by the hypothesis class. You can put it into how many pieces you want. Okay. So for instance, I don't know, if I have 3 points like this, okay, can I shatter 3 points with lines? This is a question for you. So my hypothesis are lines in 2 dimensions, and I have 3 points like this. Can I shatter them?
Yes.
Yes. Right. I can do this. This will give me, say, +1 here and -1, -1. Or I can do this, then this one is +1, or I can do this. Okay? Or I can do it like this, or like that. Okay, so 3 points in dimension 2 can be shattered by lines. Okay, what about 4 points?
No. No.
No, right? I mean, you know, it just doesn't work. I mean, I will prove it again, but okay, it doesn't work. So this D is called the VC dimension. VC dimension. Okay, for Bartnik. And now it's great because you see that your generalization is exactly up to a log factor bounded by square root of d over m. Okay, so maybe let me write it here. Okay, so corollary. For binary classification, the generalization on S of H bounded is upper bounded by some constant times square root, and then you get d log n plus log 1 over delta over n. Okay, and this happens with probability at least 1 minus delta, where d is equal to the BC dimension of H. Okay, so this, sorry, this tells you that the sample complexity, is exactly the VC dimension.
It's very hard to read the red. Maybe it's not today.
Okay, I will do something else. Right, generalization is bounded by square root d log m plus log 1 over delta over m. Okay, so it's just putting this key result with this, and I mean, it's putting everything which is on the board together. Okay, and let's just finish with this section with an example. Which is learning half spaces. Okay, so the only thing I need to do is to compute the VC dimension of those two. The claim the VC dimension of half space in dimension D. This is upper bounded by D. In fact, it's equal to D. But you only need an upper bound. Okay, so here is the proof. But first, is it clear, the statement? Okay, so the function class is this class where you just you have a direction, a normal, then you have the hyperplane, and you're predicting +1 on this side and -1 on the other side. And we want to understand what is the sample complexity of this problem. The proof is like this. So let me remind you Radon's theorem. So Radon's theorem goes like that. Any set, let's call it omega in RD with at least d plus 2 points can be partitioned into two sets, omega 1 and omega 2, such that the convex hull of omega 1 intersects the convex hull of omega 2. Okay, so I have okay. So what I'm saying is, look at those 4 points. Okay. I want to partition it into two sets such that the convex hull intersect. How do I do that? Well, I can just put those 2 points into one set and those 2 points into one set. What are the convex hull? It's this line and that line. Okay, so those 2 lines, they intersect. In higher dimension is the same thing. So look, it just works like this. So this is in R3. Clearly, I can take d plus 1 points, but I cannot do that. Take 0 and the coordinate basis. Okay, so you take 0 and all the coordinate vectors. If I partition it into two sets, any two sets, the convex hulls, they don't intersect. Okay. But if I add any other point, then suddenly I can take this, and that's it. Okay. They intersect. So now, why does this conclude the proof? Well, if I can shatter a set of points, okay, so if I have this, if I can say +1 here and -1 here, it means that the convex hulls, they don't intersect because I have a line going through them, between them. So I cannot shatter d plus 2 points. I can shatter at most d plus 1 points. Yeah. And just to make sure we are on the same page, let me explain just one last time why is this uniform generalization useful for learning, for, say, empirical risk minimization. So this is the last reminder before we move to the new chapter. This last reminder. Analysis of ERM. Okay, so ERM is just the minimizes the R min over H in H of L mu hat M of H. Right? Just have a certain hypothesis class, I don't know, neural networks, and you just take a neural network that minimizes the empirical error, assuming you can plan it. What's the point now? The point is that what is L mu of ERM? Okay, that's what we care for. Well, by generalization, I know that this is bounded by L mu hat M of ERM. because this minimizes it, it's smaller than any H star, than any other guy, H star, plus the generalization. Okay. Here I use the definition of the empirical risk minimum. And now this, again, by generalization, this is bounded by L mu of H star, plus 2 times the generalization. Okay. So that's why generalization is so useful. Okay, so that's it for the reminders. So ask me a question now. There is one on what we did yesterday. So clear. I think it's clear. So it's really
Where did the
yeah.
2 come from in the last?
But because here you see I have L mu hat, but I want L mu. So I need to say again, oh I see, because you're saying in general, okay, you're right. This would be, okay, you're right. For this I need the absolute value. Is that what you're saying? Yeah. That's true. Okay, so let's move on to the next chapter. Many places of generalization. So our current the understanding of generalization from chapter 2 says nothing about, say, training a neural network with, say, 1 billion parameters and 1 million samples. Okay. Just it says nothing because what happens is basically if you use the VC theory, essentially the VC dimension is always going to be the number of parameters. Okay, that's a good rule of thumb. So the VC dimension of neural networks with 1 billion parameters is going to be 1 billion. So everything we have seen so far tells you that to generalize, you will need 1 billion samples. But that's not how those things work in practice. Okay, so what's going on? Okay, can we answer this question? Okay, so we want to go, so need to go beyond uniform law of large numbers and take the algorithm into account. Take the algorithm into account. The point is, with 1 billion parameters, you know, we're not looking at all neural networks with 1 billion parameters. We have a very specific algorithm to navigate in that space, namely stochastic gradient descent, okay, which we're going to see today, hopefully. So we need to understand what is this algorithm doing. But then we want to have generalizations that depend on the algorithm. Okay, so that's what we're going to do now. So we'll see many things, but let me start with one. Okay, so one, we're going to talk about stability. This is after Bousquet, Olivier Bousquet, and Elisal. It's a paper from 2002. But really, some of the idea go back to Luc Devroy, and Wagner in 1970. algorithm is stable, then it should generalize. Okay. And what is going to be our definition of stability? I'm going to explain in a second. So let me start with the theorem. Let me define the stability of an algorithm. So an algorithm is a learning group on you. Let me also say, for sake of simplicity, we're going to focus on the generalization of the learning rule H on U, which is the expectation over S of the generalization. Okay, so again, yesterday we talked about concentration inequalities. So if you understand the expectation, then the next step is to do a concentration inequality to understand this value. Okay, but we won't do this next step. I want to focus on the expectation. Okay. Good. So let me define the stability. So stability is going to be like this. This is the expectation over the data, over a random element, data set, and over a fresh sample Z from the expectation of what? So you look at your loss of H bar trained with S on Zi. Okay. So this, so far what I have written is nothing but the empirical error. Okay, just the expected value when you pick a random sample of your algorithm. This is the empirical error. But now you're going to compare it to L of H bar on Zi. So the same thing, except that instead of training on S, you're going to train on S where you have removed the ith element and you have replaced it with Z. So L of H bar on S minus I, where S minus I is this thing. Z1 to Zi minus 1, Z prime, Zi plus 1, and to Zn. Okay, so I want to understand how sensitive my algorithm is to just one data point being different. And you agree, if I have a million images and I just change one image in my data set, if suddenly something completely different happens, then it's probably not a very good algorithm. And the theorem is really, it's more an observation, but okay. The theorem is this, then the generalization of H bar on U is in fact equal to the stability. So in fact, we have not done anything, but it's still a very useful different perspective. So the generalization is nothing but a stability. Yeah, I find this pretty insightful. So in particular, this is not really going to tell us. Okay, so there are papers using this to explain some stuff with neural networks. Using in particular the stochastic gradient descent. It takes random data and takes little gradient step. If there is one element which is different, then it's not going to change the output too much. Okay, so let's do the proof. So the proof, it cannot be, it's just a matter of rewriting. So the generalization of H bar on U. Again, this is the expectation over S of L mu of H bar of S minus L mu hat M of H minus L of H bar S on Zi. And here I need to sample also I at random from N. Okay, just that's the definition of L mu. You take a fresh sample and you evaluate H bar. That's the definition of mu hat N. You take a random element of your data set and you evaluate H bar. But now you see in this, when I test H bar S on Z, it's just a change of notation to swap Zi and Z. Okay, it's just a renaming, because anywhere I take the expectation, so this is equal to the expectation over S, Z, and I from N of L of H bar S minus I Z minus L of H bar Zi. Which makes me realize that I swapped with the this should be minus I. Okay, so that's the proof. Again, it cannot be difficult. It's just a matter of reality. So now, as an application, I want to discuss again regularization that we saw yesterday, Euclidean regularization. And yesterday we said that if you do for instance a least squares regression, and you add a penalty which depends on the Euclidean norm of your predictor, this regularization, what it was doing is that it was implicitly limiting the capacity of your hypothesis class. It was saying that it has a limited capacity so that the Rademacher complexity is controlled. What we're going to see now is that adding this Euclidean regularization, you can see that as making the algorithm more stable, okay, which directly implies generalization. So application. Regularization as a stabilizer. This was clear, by the way. So consider the following. Let's say you train an algorithm. So now we talk about weights, like we did last time, which is the argmin over W, let's say RD of L mu hat M of HW plus lambda times the Euclidean norm of W. So you take a certain loss function and you regularize it. This could be least squares, this could be logistic regression, hinge loss, whatever you want, and you regularize it. Okay, and we're going to assume that we're in the complex case, where W maps to L of HWZ is convex and Lipschitz. Okay, and this, to clarify, this is W hat of S, okay, of a certain sample S. Now what I want to say is that this term, this regularization term, it's making this algorithm stable. So let's see that. Okay, so what is the stability? So the stability say on S of W I. Maybe I should call it W and of W bar S minus I on Ti minus L of H W bar S Ti. Right, I just introduced the empirical notion of stability. So the real stability is when you take the expectation with respect to S. Okay, so this is a generalization. It's nothing but a generalization when you take the expectation over S. So because this is Lipschitz, this is upper bounded by the expectation over I of the norm of W bar S minus I minus W bar S. Okay, so stability is just asking how is this weight vector changing? Is that the norm of W bar S minus I minus W bar S. This is going to be bounded by 2 over lambda n. So this means the algorithm is stable because of the lambda. Okay, if lambda was 0, there would be nothing, but if lambda is non-zero, then there's something. Okay, so before I jump into the proof, I want to make sure we agree on what's going on and what we're doing. So the intuition, the insight for why this is like this. So let's call this thing subjective function, let's call it Fs of W. Okay, so this is what we're trying to do. So this is our view. Okay. And I don't know. This is Fs of W. Okay. And this, the minimizer, this is W bar of S. Okay. Now what happens is that I'm changing F. Okay, when I try to obtain W bar of S minus I, I'm changing my objective function. I'm replacing one sample by something else. Okay, so I would get something different. Something like this. This guy is F S minus I W. The point is that this distance, these are small. Why are they small? My loss, it takes value between 0 and 1. Okay, that's what I assumed at the beginning. So at most, these distances are at most 2 over n. Okay, I'm going to reprove it to be clear. But these distances are small. Okay. So this distance is small. But now, because of the lambda term, I want to say that small distance like this implies a small distance like that. Why is it? Well, if this is small, okay, then you cannot be too far away because this thing is strongly convex. So it's curving like a square. So as I move away, this goes up, 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 up. Okay. So it cannot, I can only go so far if I want this distance to be small. So this is stability. Okay. So stability comes directly from adding the regularization. Okay, so let's do the proof, but this is it. Okay. So just let me, for notation, equals, we're going to denote W is W bar S, and W prime is W bar S minus I. Okay, so first thing I said is what is F? Let me see just how I want to write it. Yeah, so first thing I want to say is that this distance is small. So what is Fs W prime? Minus, let's see, what do I want to say? Okay, so let's look at this objective function. Okay. So this thing is larger than lambda times the norm of W prime minus W Euclidean norm squared. Why? This is lambda strong convexity. Okay, again, it's just the fact that W is the optimum of Fs. Okay. So as I move away from the optimum, this term is growing like a square. So, and this term, it can only grow. So what happens is that this distance is at least lambda times the Euclidean norm of W prime minus W squared. Okay. If you want to prove it, it follows from strong convexity. On the other end, what is this? It's equal. So let me introduce Fs minus I of W prime minus Fs minus I of W plus something. So what do I have to put? So I have to put 1 over m, and then what do I get? I get difference between those two. So I want L of W prime on Zi minus L of W prime on Z prime. And then I get this minus 1 over m of L of W on Zi minus L of W on Z prime. This is equal to that. Now this thing is negative. This is negative because W prime is a minimizer of F S minus I. And what is this? By Lipschitzness, you see, this is bounded by the norm of W prime minus W over M. And I get it 2 times. So this is bounded by 2 over M times the norm of W minus W prime. Okay, so I get lambda times the norm squared is bounded by 2 over m times the norm. So the norm is bounded by 2 over lambda m. And these equations are nothing but the rewriting of this picture. Is that if I look at mu of lambda regularized empirical discrimination, this is going to be bounded by mu of let's say some W star plus lambda norm of W star squared plus some constant times the stability, so some constant over lambda m. Okay, so here to write this, I just use the fact that I use the generalization. So I use that mu of lambda regularized DRM, it's close to L mu hat. Okay, so the proof, let's do L mu of lambda reg DRM. This is bounded by L mu hat M of the same thing, plus the generalization, which is bounded by L mu hat by, let's say, Fs of W bar S plus the generalization. Okay, because Fs is just this plus a positive term, which is bounded by Fs of W star plus generalization, which is bounded by L mu of W star plus lambda times the norm of W star squared plus 2 times the generalization. And the generalization is a stability, which is this. So we get this statement. Now you see, if you optimize over lambda, and let's say that the norm of W star squared is less than R squared, then you exactly get an error, a regret, which is of order, when you optimize over lambda, we get the geometric mean of those two things. So you get R over square root n, which is exactly what we had obtained yesterday with the Rademacher complexity. Okay. So this is just a different way to obtain the same result. From the Rademacher complexity point of view, you remember we were limiting the capacity. So we were saying we are searching over W's of small norm. Now here what we're saying is that we're penalizing. And these are the same two things we said yesterday, but there was this implicit relation. But now you see that the lambdas that you should take, well, it's coming from this optimization perspective. Okay. Yeah.
So here the W star can be any arbitrary W as long as the norm is bounded by the R square.
Yeah.
But then I'm wondering whether the last inequality that we get, like whether the right hand side can just be like arbitrarily large, and how useful that is in practice. So why do we want to bound it by an arbitrary W?
So this is true for any W.
Yeah.
So what you want, you will find a W which trades off between the two.
Okay.
So it's, maybe there is a super complicated W, meaning a very large W, which is very good. But this is not attainable because this will be a bad bound. This one is exactly telling you have to trade off. Maybe there is a very good W which is very big, very complex. Okay, you cannot get that one. What about something a little bit simpler? You still get something good. That's the way to.
But so should I interpret this as an upper bound on the loss of the regularized DRM?
Yes. That's how you should interpret it, yes. Remember, this assumption, that's a way to limit your concept class. You remember that, right?
Yeah.
This is your inductive bias, that you have a limited concept class.
Okay.
But it's not anything, it's not arbitrary.
So really we should look at the right hand side with W star that essentially minimizes the right hand side.
Yeah, exactly. Yes. Yeah, and here I'm being a bit careless because from this to this, it's not really the generalization of the algorithm, but it's a generalization for a fixed W star, so it's just trivially true. I don't want to dive too much into those. Okay, any other question on stability? so the next one that I want to talk about is robustness. So I don't know if did you already talk about robustness? No. So this is a very popular topic in optimization, and we will see that it also allows to bound the generalization. So stability is about some kind of robustness. Robustness to changes in the training data. Robustness is about change at test time. Okay. Meaning that it is on a fresh sample. So the question is, what if the sample on which you're going to test is of a slightly different distribution? Do you get something, completely different, or do you get something still reasonable? So it's really a different notion of stability. You can be robust with respect to this and not stable, and vice versa. These are two different notions. This one is really gaining traction these days, and I will talk more about it tomorrow. The problem is like this. So you know about autonomous cars, that are out there in the streets. And so what they do is that they have these deep networks that try to interpret the image. And imagine that you're running towards a stop sign. You want your network to realize that there is a stop sign, okay? And it does it very well. But now, what happens if you have a stop sign? Stop. And somebody puts a little sticker here. But it's a very malicious sticker that was designed, having the neural network in mind. So that when the neural network sees this, this is not from its training data. This is from a different distribution. But when it sees this, suddenly it predicts that, I don't know, there is a gun, or that there is no stop sign. It doesn't see the stop sign. This does happen for real. And it's a real problem. It's an open problem. We don't know how to deal with it. Okay. So it's really about robustness at test time. And again, we'll talk more about it tomorrow. So what I'm going to do now is that I'm going to assume that you have a robust algorithm at test time, and show to you that this is enough for generalization.
But
Yeah.
in this case, because you mentioned this adversarial attacks, are we talking about robustness where you're trying to fool the network or the algorithm, or are we talking about small perturbations in your test?
Right. So you will see. I'm going to tell you. So it's not an easy answer to your question. What I'm going to tell you now is a certain definition of robustness that works for generalization, and tomorrow we'll talk about other definition of robustness. Okay. So this is after a paper by Chu and Manor from 2010. Okay, so here is a possible definition. And I emphasize the possible definition. I'm not saying this is the best, but it will allow us to do some nice mathematics of robustness. So assume that the sample set Z can be partitioned into K sets Ck from 1 to capital K, such that the following holds. if I have a point z and a sample point zi in the same set ck, then the loss of my algorithm of S, and let me see which zi minus L of h bar S z. This is smaller than some epsilon. And I'm going to allow my epsilon to depend on the sample S. Okay, so again, the picture is like this. So this is Z. Or just think about it as X. I can partition it into case set, such that if I have, this is a true sample point Z, and I have another one Z, then my algorithm is not changing its, the performance of the algorithm is very close on Zi and on Z. Okay, so I will give you some examples just to. So example. Well, the most basic example is really when H is Lipschitz. So if H bar is 1 Lipschitz, then one can take K equals the covering number of Z equals of radius epsilon. And this is in a sense the main example. So you remember we talked several times about the complexity of the hypothesis class. And I danced around the question, is it a number of hypotheses in it, is it whether they are Lipschitz or not, and if you say that it's a complicated answer, all of these answers are valid. But here you see robustness really tells you that if you output something Lipschitz, then something good is going to happen. So this is robust. Okay, so again, this is robust. This is not robust. A closely related one, which is just about Lipschitz in a different metric, but I will still say it, is a large margin classifier. And we'll talk about margin again. So this means, say, H bar of X is equal to H bar of Xi for any X which is gamma close to Xi. Okay, so imagine that you're just trying to predict zeros and ones, and what you have is something like this. Okay, and there is some margin. Then you see if there is this margin, let's call it gamma, then I know that any of my training data point, I can perturb it by gamma, and I won't change my decision. So if I have a margin, then I'm robust. Okay. And K is bad, capital K. The size of capital K is big, but still, give you something. Again, with our neural networks example, you can see that the robustness is not at all going to depend on the number of parameters. It's going to depend about whether the network is Lipschitz or not, which is something completely different. Okay, you can have unlimited number of parameters and still be Lipschitz. Okay, so it's telling us that generalization can be about something completely different. Okay, so now here is the theorem. So let's call this K epsilon robust classifier or robust algorithm. satisfies the following. So generalization of H bar, this is upper bounded. Let me get my constant right. By the expectation over S epsilon S plus square root k over n. So you see that now the sample complexity up to the robustness depends on the number of partitions that you number of this is your sample complexity. And I wrote an epsilon S because actually a stronger theorem is valid. Again, I don't want to get into concentration, but in fact the empirical generalization on the sample is bounded by this epsilon S, the robustness on the sample, plus some constant times square root k plus log 1 over delta over n. And this is with probability at least 1 minus delta. Okay, so again, here it's a concentration argument which we won't do. We will only think about the expectation level. Any question on the statement before I jump into the proof? Yeah.
So k and epsilon are both scalars,
No.
or epsilon is a function
K is a scalar and epsilon is a function.
that will give you the right
Yeah,
hand
yes,
side.
that takes a data set. No, yeah.
Is this always defined?
What?
So is the expectation of epsilon always finite?
No. So, okay. Very generally, you have asked two times a question which is similar, and I want to make sure that I answer it properly. In general, in learning theory, you have bounds like this. You have a left-hand side that you care about, and you have a right-hand side. It could be that the right-hand side is meaningless, in which case it just means, okay, the algorithm does not work. It just nothing happens. So it's only in situations where the right-hand side makes sense that this is interesting. For the right-hand side to make sense, you want the algorithm to actually be robust, meaning this thing is small, meaning this expectation will be finite. So that's a way to think about those things.
Is it automatically so that the right-hand side is infinite, that the algorithm doesn't work, or is it just that you cannot say anything about it?
No. It just says that you cannot say anything about it via this route. But again, one of the points of this course that I want to make clear is that generalization, you can really view it from many different sides. And traditionally it was thought through the VC dimension, mainly, but this is definitely not valid for modern machine learning, where we're dealing with this very large hypothesis class, but we're only exploring a tiny fraction of it. Okay, so let's do the proof. So let me denote that nk is the number of samples that falls into the partition element k. So nk is the size of the intersection of S with ck. Note that in expectation, the expectation of nk is nothing but n times mu of ck. Right? So now, what is L mu of h bar? Okay, so this is the expectation over z for mu. L of h bar on z, which I'm going to decompose as whether z falls in one of those partition elements. So this is the sum of k equals 1 to capital K of the expectation of L of H bar Z, expectation over Z, given that we consider times mu of Ck. Right, I just decompose my expectation. Okay, so it's the sum of the expectation given that you're in Ck times the probability of being in Ck. So this I can write as the sum K equals 1 to capital K of the expectation. So where do I want to go? I start with L mu of H bar and I want to get to the empirical estimate. So what do I get? I get mu of Ck, we just said it's 1 over n times the expectation of Nk. So let's write it like this, 1 over n, and let me replace mu of Ck by Nk. So I get Nk times expectation over Z of L of H bar Z, given that Z is in Ck, plus the difference, the sum equals 1 to capital K of mu of Ck minus Nk over n times this expectation. Now, why did I do that? Well, I did this because this first term, up to the robustness, it's exactly the empirical loss. Because you see, whenever Z is in Ck, I can replace it by Zi, by any Zi which is in Ck. Let me write this. First two is that 1 over m sum K equals 1 to capital K of Nk expectation over Z of L of H bar Z given that Z is in Ck is upper bounded by 1 over m sum for I equals 1 to m of L of H bar Zi plus epsilon s. Right? Because you see, in this sum, I have Nk terms which are in Ck. So all of them I can replace it by any other Z in Ck by the robustness. So this inequality just follows from this. So now I get that this is upper bounded by epsilon s plus L mu hat m of H bar plus this term. So this is the first key. And this term I'm just going to upper bound it by the sum of the absolute value plus the sum of K equals 1 to capital K of the absolute value of mu of Ck minus Nk over n. Okay, I just use that this is bounded by 1. So now I will need to bound this term. And that's the second key, which is very simple. This is the second key. So notice that so far I have not taken the expectation over S. Okay, so now I'm going to take the expectation over S to control this thing. No, just think for a minute. This should be small. Right? If mu of Ck is large, then this should concentrate very closely around this value. And if it's small, then it's just smaller. So this is a simple argument. So let's look at this. What is the expectation of mu of ck minus nk over n? Okay, so we don't like absolute values, we don't like first moments like this, but we like second moments. Okay, because variance and all of this. So let's upper bound this by square root of the expectation of the square, mu of ck minus nk over n. What is this? This is nothing but, this is the variance of nk over m. Right? The expectation of nk over m is mu of ck. Okay. But what is nk? Nk is sampled from a binomial with m trials and probability of success in mu of ck. Okay. So the variance of nk certainly bounded by n times mu of ck. And the variance of a binomial is m times p times 1 minus p. This is the variance of this thing, because there is a 1 over n which is going to cancel with this n. This thing is bounded by mu of ck over n. Which we are pretty happy about, because this is small, okay, which was our intuition. Now just one step of Jensen and we're done. So last step, so sum for k equals 1 to capital K of the expectation of mu of ck minus nk over m. We just proved that this is bounded by the sum for k equals 1 to capital K of square root of mu of ck over m. So the sum of the square root, this is bounded by square root of the number of terms times the sum of those terms. So this is bounded by square root of the sum of k times the sum for k equals 1 to capital K mu of ck over m. The sum of the mu of ck, because it's a partition, this is 1. So this is equal to square root k over m. Okay, so this concludes the proof. Is there a question on this? So we have seen so far 3 different ways to deal with generalization. Uniform law of large numbers, which basically tells you that the sample complexity is the number of parameters describing the function class. We have seen stability, meaning that if you have an algorithm that does not depend too much on a single data point, then it's going to generalize. And we have seen robustness, which means that if you have an algorithm which does not change its decision too widely, which is pretty Lipschitz, then it generalizes. And we will see tomorrow, I went a bit slower than I expected, but we'll see other things. So we'll see 3, there will be an information theoretic perspective. Where we will say generalize if do not memorize data too much. Remember, one of the first thing I said is that just memorizing your data is not really learning. And what we'll see is exactly that if you don't memorize the data too much, if from the hypothesis I cannot recover the data set, then you will generalize. Okay, so this will be nice. Then we will see another thing, which is this back-base generalization. So I don't want to explain it now, but it's a different way to generalize. And then we'll talk about online learning, which is yet another way to generalize and which goes beyond the IID model, where you don't need to assume something about the data. So tomorrow we'll do those three things and then talk a little bit more about robust machine learning and